Okay, hi guys. So long time no see, and it's been actually so long that I have to find my recording equipment. Well, usually it used to be just connected to my laptop at all times, but this time I had to find it. So today I'm going to do this editorial for this Atcoder Beginner Contest 206, and I have solved all of the problems, and we still have some time left. Yeah, so I'm going to make this video and I'm going to upload this. And I know a lot of people don't participate in Atcoder beginner contest, especially a lot of my audience, but they really should because these are really good for beginners. And even if you're till the purple level, you'll get to learn a lot from these. So let's start with this problem A. Yeah, so this is actually pretty straightforward, and what like we've been told exactly what we have to do. We just want 1.08 into n rounded down, and we want to see if it is equal to 206 or smaller or greater, and based on that we have to print something. So the only thing that I would like to say here is, instead of doing something like n into 1.08, it is obvious, which involves double. So this involves double data type, so it is always better to do something like n into 108 by 100, because there's no chance of overflow also here. So yeah, so n into 108 by 100 is definitely better, and this does not involve double, so it only involves ints. So that's why we can say that m equals this thing, and then we can just check if m equals 206 or smaller or greater. So that's exactly what I did in this problem. How can I see my old submission? Somewhere here. Okay, okay. Right. So this is the code. Yeah, n into 108 by 100, that's x, and just check if it is smaller, greater, or same. So now I have this problem B. Yeah, even this was simple. So what's happening is, on the first day you get 1, on the second day you get 2, and the third day you get 3, and so on. So we can say that on the kth day you will have k into k plus 1 by 2, right? Because this is like an AP, this sum 1 plus 2 plus 3 plus 4 till k, and this thing equals this, k into k plus 1 by 2. So we already know that, but how are we going to use this? So there are a lot of ways to actually use this, but the easiest one here is that we know that this is of the order k square, right? So this is like O of k square, and we want this thing to be greater or equal to n. So we know that this will be close to, like, the k that we have will be close to square root of n, right? So k will be close to square root n, like of the order of square root n. In fact, it is 2 into square root n or something. But yeah, so since n is only 10 to power 9, we can easily say that k will be smaller or equal to 10 to power 5, or even 5 into 10 to power 4, I think. Don't need We don't need an exact bound here. We can just see intuitively that it is that k cannot be very big, right? So if k is not very big, then what we can do is we can just iterate on k from 1 to like till wherever it is required, and at some point we will definitely find the correct answer. So you can see here, this is my code, and yeah, so this is like a simple brute force solution. Just take n as input. So this is the formula. We want x into x minus 1, x into x plus 1 by 2 to be greater or equal to n. Actually, this should be plus. Yeah, but anyway. So, so what I'm doing is, I have a variable total and I'm adding I to it. And whenever it is greater or equal to n, then we print I and just exit, just return end of the loop in the end of the program. So yeah, so that's what we want to do. Just keep iterating on the days. What I'm trying to say is, the answer won't be too big, so you can just keep iterating on it and easily find the answer. Then you would ask what to do if n is like of the order 10 to the power 18. So there are multiple things that you could do here. One is simply do a binary search. So what you can do is, instead of doing a linear search, you can do a binary search. And the other thing you could do is you could actually find the square root of n and multiply it by 2, and then after that you will need to add or subtract only a few values. So yeah, so that's also another way, and maybe that's the fastest. Okay. Okay. Now we have the problem C. Yeah, this was also easy. So in this, what we have to do is we are given an array A, and we want the number of pairs such that AI not equals AJ. So I think I did something a little tough here, but what you could do is you could first find the number of pairs such that AI equals AJ and then subtract it from the total number of pairs. So we know that in n numbers, the total number of pairs will be n into n minus 1 by 2. And then what we can do is we can find the count of each element and subtract it like this. Subtract count into count minus 1 by 2. Right, so this sigma means the summation, obviously. Right, so we need a count of each element, and this we can do by storing it in a map. So we can have a something like map of int comma int count, something like this. So we can do that, and I think that should work because that's how it works. So 3C2 is like 3, and 1C2 is 0, and 2C2 is 1. So 3 minus 1 is 2. Yeah, so this would work. Yeah, so this is like the formula, and this would work. I'm not going to show my code because I complicated it a little more. So what I did is I actually tried to find AI not equal to AJ. So for that, what I did is I used some other type of formula, and it would look something like n minus count. These are the elements that are not equal to my current element, multiplied by the count, and then divide by 2. Yeah, something like this I did. In fact, just have this summation and divide it by 2 in the end. I think that's what I did. This is like saying elements that are equal to a current value and not equal to, multiplying both of them, because those many pairs we can make. And since I has to be smaller than j, that's why we divided by 2 at the end. Okay, let's see. Let's see the code. I think something like this is what I did. Yes, I have the map of counts, then I iterate on each element, and yeah, so that's what I'm doing. I'm just adding n minus count into count and dividing it by 2. So yeah, so that's also a way, but I think this one is simpler. Find equals and subtract it from total. Okay, so now we have this D problem. Okay, so this one is actually pretty easy, and what we have to do is we are given a sequence, something like A1, A2, A3, A4, A5. Let's say there are only 5 for now. Okay, and in one operation, what we can do is we can change all the ones into twos. So all ones will become twos in the entire sequence. Like all the X will become Y, right? So something like this we can do. So the obvious thing here is we have to pair these two up, and we have to pair these two up, and this one is loner, so we can ignore it. If the sequence length was even, then this would not even exist. But yeah, anyway. So what I'm saying is, if this is like 3 and this is like 7, so obviously we have to convert all threes into all sevens, or we convert all sevens into all threes. So that's the same thing. So kind of like what we're doing is we're saying that 3 and 7 are the same thing. We have to say that 3 and 7 are the same thing, and we want to do these operations minimum number of times. But uh, like, what does minimum even mean? Obviously we have to do this operation here, and we have to do it here, and so on. So obviously we cannot do it less than that. So yeah, so that's how we will find the minimum. We can just put all the values here. So let's say this is like a 3, this is like a 7, then again 3, then 7, something like this. So we like when we process this thing, we know that 3 and 7 are the same thing. So when we process this, we don't have to do anything because we already know that 3 and 7 are the same thing. What we can do is we can use DSU, that is disjoint set union. So we can use disjoint set union. You can also do it with graph, but I would recommend disjoint set union. That will be easier. So what I will do is first I will check if 3 and 7 are in the same set or not. So if they are already in the same set, then I don't do anything. But if they are in different sets, then I will just join them and like union their sets, and that's it. So I just have to count the total number of times I perform a union. If you want to do it with graph, what you can do is you can actually find the total number of connected components and then do something with it. Or like make spanning trees everywhere and find the edges. So that's a little more complicated. DSU is the best. And let me show you my code also. This one is pretty intuitive, I think. So yeah. So I have some DSU snippet or something. What I'm doing is I'm taking everything as input. I am pairing the first element with the last element, the second element with the second last, and so on. So I'm pairing I and j, and I'm just unioning, like I'm performing the union of I and j. That is the like the let's say xth element from the beginning with the xth element from the last. I'm just merging them, and I have this answer plus plus here. So this part just checks if they are already in the same set or not. So if they are already in the same set, then I return and don't do anything. But if they are not in the same set, then I will perform the union, and I will also add one to the answer. So this way the answer will increase, and I'll just print the answer at the end, and yeah, it works. Okay, yeah. So these two problems are actually a little bit tough. So yeah, so let's look at these. So this one so a little hard to explain. Yeah, so the thing I thought here is we are given L and R, and what we want to do is we want to see the pairs of x comma y such that they lie between L and R, and these conditions should satisfy. So like if their GCD is G, oh, okay, I have to change the name again. Yeah, so if the GCD of xy equals G, then we want G not equals 1, and we want x not equal G and y not equal to G, right? So what does these two mean? So if x equals G or y equals G, then this means that x divides y or y divides x, right? This notation means that x divides y. This means that y divides x. So we don't want this, and we don't want them to be coprime. What we can do is we can again find the total pairs. So the total pairs will be like r minus l plus 1 square. So these are the total number of pairs. And from this we can subtract the coprime pairs. Subtract coprime pairs. And once we subtract coprime pairs, we will get all the pairs with this condition satisfied, that their GCD is not equal to 1. So if the GCD is not equal to 1, what's remaining? That these two conditions could still hold, right? So what we want to do is we want to eliminate this as well. So how can we eliminate this? We can do something like we can kind of do something like iterate on all the multiples of x and all the multiples of x in the range L comma R. We can iterate on them, and like if we find any multiple in this range, then we can say that let's say if we find a multiple k, that k is a multiple of x, so we can subtract two pairs from here, that is xk and kx. Unless k and x are equal, then in that case we can subtract only one. So basically the only bottleneck here is this part, how to find the coprime pairs, right? So for this what we do is we kind of use a thing called inclusion exclusion. So our problem is just we are given a range L comma R, and we want to find coprime pairs in this range. Coprime pairs in this range, right? So yeah, so my writing is actually very bad, but yeah. So we want to find coprime pairs in this range. So what that means is we want x comma y in the range L comma R, and we want GCD of x comma y equals 1. Right, to do this, we actually use something called inclusion exclusion, or like you can also call it Mobius inversion. So we use a thing called inclusion exclusion, or something like Mobius. Like, you just use the Mobius function, right? So the idea is something like, to find the numbers which have GCD equal to, like, to find the numbers that have GCD equal to 1. What we want to do is, we want like to find the numbers with GCD 1. Let's call them G1, right? So like to find G1, let's find um, M1. So M1 are the numbers who are multiple of 1, right? So like these are the pairs such that both are divisible by 1. So what I'm trying to say is, I'm saying M of K means that number of pair XY such that um, like both X and Y are divisible by K. So this means that K divides X and K divides Y. Okay. So we know that M1 is definitely greater or equal to G1, because like obviously if the GCD is K, then or in fact MK is greater or equal to GK. What I'm trying to say is, if the GCD is K, then obviously they both have to be multiples of K. So yeah, so something like that would happen. So I won't explain it in much detail, but it was something like, if we actually want to find if we want to find GK, it is something like MK minus M of 2K minus M of 3K plus M of 6K, and so on, right? So what I'm trying to do is, I'm saying that obviously I have to add MK, but 2MK kind of gets added twice, because like if they both are multiples of K, multiples of 2K, then they are multiples of like obviously they are kind of getting wait a second, I want GCD equals 1, right? So I will do M1 minus M2 and M3, M6, and so on. Anyway, wait a second. So to get G1, I want M1 minus M2 minus M3 plus M6, and so on, something like this. So this is just inclusion exclusion. And what I'm trying to say here is that to get the numbers with GCD equal to 1, we will obviously take the numbers which are multiples of 1, like we want both of them to be multiples of 1. But if both of them are multiples of 2, then that's a problem, because then GCD won't be 1, right? For example, if we have a pair 2 comma 4, we know that both of these are multiples of 1, but they are also multiples of 2. So obviously we have to subtract M2 here. We will subtract M2, we will also subtract M3, but something like where both are multiples of 6, like if we have 6 comma 12, so we have subtracted this for M2 also, and we have subtracted it for M3 also, because they both are multiples of 2 also and multiples of 3 also. So we have to add it once again. So that's why we add the M6, and similarly we subtract M5, then we add M10 and M15, and then we subtract M30, and so on. So something like this we do. This is like a inclusion exclusion thing. But how do we actually find these coefficients, whether it is plus or minus for each number? And for some numbers it is 0, like if we have M4 or M8 or anything, so these are all 0. So like the coefficient for those is 0. So like here we have negative, here we have positive, and so on. So this is actually done using something called the Mobius function. So this is done using something called the Mobius function, which is like, it sounds a little scary, but it is simple. There are just 3 cases. if the number has any prime square as a divisible as a divisor, like if the number is of the form 2 square multiplied by something, multiplied by 3 into 5 or anything. In this case, this becomes 0. You can see that we don't have anything like M4 or M8 or M12 or even M9 or anything. So if you have the square of any number, or if the divisor is the square of any number, then obviously it won't work. So for that, the Mobius function is 0. That is, the coefficient in this series is 0 for that element. And then if we have everything square free, that is, in the prime factorization, all the prime numbers that are there, if none of them have any square, then what we can do is we can say that if the number of prime numbers, so number of prime factors, okay, if this is even, then this is 1, and if it is odd, then it is -1. So this is just pattern finding from here. If you kind of find a pattern from here, you will get this exact pattern. This is called Mobius function. There are a lot of other properties about Mobius function, like it is actually a multiplicative function, so you can actually find it using linear sieve or something like that, which is what I have done here. But you can just use these things directly, find the prime factorization of all the numbers in the range, again using linear sieve or something like that, and yeah, it will work. So yeah, so that's something you could have done. Let me show you my code. This one was a little tough, by the way. Okay. So this is actually a code which finds the Mobius function, and then I have actually made a function that returns the Mobius function of x. So like mob of 1 will be 1, 2 will be -1, 3 will be -1, and 4 will be 0, and so on. Then what we do is, till this part, what I'm trying to do is, here I'm just finding the total number of non-coprime pairs. Okay, so once I find the non-coprime pairs, what I want to do is I want to iterate from L to R, and all the divisor pairs I want to subtract them twice. And one thing I have made sure is that, yeah, so I'm subtracting it twice because we have two pairs, xk and kx both. But if x equals k, then we have to subtract it only once. So that's what I'm doing, subtracting it once. And if I and j are not equal, then I'm subtracting it once more, and yeah, printing the answer. That was the problem E, and now we have problem F. So yeah, so this one is also a little tough. I think this is actually a lot tough. Like for me, it was not that tough because I know this theorem called Sprague-Grundy theorem. So obviously, I'm not going to teach that here, but that's something you need to know. So yeah, now this is a game theory thing called the Sprague-Grundy theorem. I don't really think you can do it without knowing this. So yeah, so that's the point. You have to know the Sprague-Grundy theorem to be able to solve this problem. So I would say kind of you should read this, or at least comment in the comment section if you want me to make a video on this. I'm not very free these days, but someday I might make it. So yeah, so you need to know this, and now I'm assuming that you already know the Sprague-Grundy theorem, and now I'm going to explain this problem. Right, so this problem is something like you can consider the interval 1 to 100, and then you have a lot of half open intervals. I didn't really see them as half open intervals. What I did was I immediately subtracted 1 to R, and then they are completely closed intervals. Yeah, so something like that we can do. And then what we want to do is, so we have a lot of intervals here, right? Like this, and so on. So in the first move, what you will do is you will take one of the intervals, and what will happen is once you take the interval, this thing kind of gets divided into two parts, right? Now this part is a separate game, and this part is another game. So yeah, so our game gets divided into two parts whenever you take a segment. One of these parts might be non-existent. In this case, like if you take this range, then it is then this part is non-existent. So yeah, so you can have like you can either take the full thing, then obviously you win, or you can divide it into like 2 new games, or maybe just 1 new game, right? Something like that. So maybe there are 0, 1 or 2 new games. Let's consider the general case when there are like 2 new games. What will happen is you have to play both of these games, and like our single game gets divided into 2 different games. So let's say we want to find the Grundy value of this. So let's say we want to find the Grundy value of this. Grundy, or it is also called Nimber, right? So obviously you should know the Sprague-Grundy theorem to understand what these Grundy or Nimbers mean. So to find the Grundy of this whole thing, what we want to do is we want to consider all our options that are valid. And why am I saying valid? Because when we are in like a little smaller range, then we could have an interval that does not lie fully within it. So obviously we want to take only the intervals that lie fully within it, and those are our options. So what we want to do is we want to take max of all the options, right? So that's how Sprague-Grundy theorem works. So max of all options we want. But how do we find the Grundy value of a certain option? So here we divide it into 2 parts. So what we can do is we can kind of solve it separately for the 2 parts. And after that, since we have 2 independent games that we are playing simultaneously, what we can do is we can take the XOR of both the Grundy values. And that's how we get the Grundy values of these two combined. And then we can take the max of all the options whose Grundy value we can get by XORing all the new games that we form. So taking this idea forward, what we can do is we can kind of come up with a dpxy. So dpxy means that we have the range x comma y. We have to play it in this range. So play in this range, right? So we have to play in the range x comma y. Obviously, our answer will be like I think dp 1, 100, right? And what we want to do in this range is that we want to find the max of the Grundy values that are present here. So once we find the max of the Grundy values, yeah, so that's all we have to do. So yeah, that's the problem. We want to find the max of the Grundy values. Okay, so contestant ended. Yeah, let me show you my code. It's not very difficult. This is just DP, and you can do it like recursively or iteratively also. In iterative, you have to make sure that the order of evaluation is correct. I like to iterate on the width first. You can do it however you want. Probably iterating on the width is the best. Right. So first I'm iterating on the width, then I have x comma y, and here I'm trying to decide who wins x comma y. This is exactly not exactly who wins x comma y. I want to find the Grundy value of x comma y, and that's what I will store in dpxy. And at the end, I will just print if dp of 1, 100 is like not 0, then Alice will win. Otherwise, Bob will win, because obviously we know that 0 is the losing state and all other Grundy values are winning state. So what I'm trying to do here is so this is actually a set in which I am storing which Grundy values I have seen till now. So this is like like obviously if I use a set, I will get an extra log, and that's what I wanted to remove. So just take a vector and yeah, so go through all of the wait a second. Go through all of the segments that are the half open intervals, which I have converted into fully closed intervals. So go through all of them and just see if they lie fully within our range or not, right? So if they do not lie fully within, then just continue. Otherwise, if they lie fully within, then find the Grundy value for this option, Grundy number for this option, and let's start with g equals 0, and then see if the left part exists and the right part exists or not. So these are the checking for the cases where we had something like this. This was the original thing, and if we divide it like this, then we don't have any left part, and here we don't have any right part, and so on. So yeah, if it exists, then XOR it with G, and then I can say that this Grundy value has been seen already. So then I run this loop from 0 till 100 or something to find the what is this? Wait a second. Yeah, to find the max, right? So whenever whenever this is not zero, that means that we have found the max, and that's what I'm storing in here. And yeah, then I'll break because max is the minimum excluded. And based on that, I can print Alice in Bourne. So yeah, so that's how this problem would be solved. I would highly recommend you to read about this Sprague-Grundy theorem. I will pin it in the comment section, so you can check that out. And in case you want me to do a video on it, let me know by replying to that comment or writing another comment. And like this video if you like the video, and subscribe to my channel if you want to subscribe to my channel. Okay, yeah, right. Thank you for watching.